Let's now conclude this lesson. So the next lesson will be the last lesson, and we'll make a conclusion for the whole course, the paradigms we saw and how they situate themselves in a more broader view of all programming paradigms. But for this lesson, let's conclude the theme of concurrent programming. Let me start by concluding what we learned about deterministic data flow. So first of all, deterministic data flow is a very simple paradigm for concurrent programming. It generalizes functional programming. It has a very nice property, no observable non-determinism or no race conditions. And in fact, all the functional programming techniques generalize to become concurrent programming techniques, which is very interesting. You can, in fact, take any book on functional programming and look into the different ways that things are done and give them a second life, a second meaning in terms of concurrent programming. So that's the first point. The second point is the simplicity, is that concurrency transparency. The fact that you can add threads at will to a program without changing the result. In fact, what you're doing is removing roadblocks and making computation more incremental, so you're able to calculate partial results even if you cannot calculate the full result. Remember in the CMAP example where we're able to calculate that the output is a 4-element list even though we don't know what the elements are of this list. Also, the computation is more incremental. This is a basic property of streams. A stream is a list with an unbound tail. If you add an element to an input stream, the computation can add an element to the output stream. This is extremely incremental, whereas if you use standard list functions, you have to give a complete input list before you get an output, any output at all. So things are much more incremental. So all of this is so easy that I call it concurrency for dummies. It means that you can basically use threads as a very simple way of managing the flow of your application and how the results are done, with what kinds of partial information you get results and so on. So that is very important, and in fact it points toward the fact that threads should be cheap. The language should have very inexpensive support for threads. It should be possible, for example, to put extremely small computations inside of threads if that's necessary, and it should still be efficient. Okay, so that's the second point. The third point is the default, is the context of deterministic data flow in the larger context of concurrent programming, where non-determinism is an important real-world property, and your program must handle non-determinism at certain points. So the point there is that non-determinism should not be the default. It should not always be available in your language. The default should be deterministic, and you should be able to add non-determinism only where you need it and nowhere else. So for example, in the client server, that is at exactly one point. It's at the point where the server accepts messages from a client. That's the only point where you really need non-determinism. Okay? So in this regard, deterministic concurrency is seeing a kind of resurgence now. It was neglected for several decades since it was invented in the 70s, but nowadays that things are becoming much more parallel in the computing world at both large and small scales, cloud computing and multi-core, at both ends, at both extremes, we are seeing a resurgence of deterministic forms of concurrency, and this is a very good development in my view. So what can I recommend to you if you want to learn more about concurrency? Well, there's two directions. One, paradigms that can avoid race conditions, and the other, paradigms that can express non-determinism. So we saw deterministic data flow. If you think that's an interesting paradigm, if you're intrigued by how that development can go on, you should look at the lazy deterministic data flow paradigm, which adds more abilities and keeps all the good properties, and even more sophisticated computation models such as constrained programming. And then I would like to mention some others. For example, the model of the E programming language, which is a secure, distributed, capability-based programming language, which offers you guarantees in terms of language security. Simple reasoning can guarantee things, and deterministic concurrency is an important part of that. And since security is very important, this is a good direction to look at. On the other side, if you want to express non-determinism, then the up-and-coming model now is message passing concurrency, and the two most successful industrial versions of that are Scala and Erlang, which I suggest you use and look at. For shared state concurrency, the successful view of that is transactions, and all the research going on distributed transactions in terms of faults based on things like eventual consistency. How do you marry transactions with distributed properties and so on? That's all very good. There's also the concept of monitors for shared state concurrency. This one I don't recommend for new systems, but if you have legacy systems, you of course have to look at it. Finally, let me give you my opinion on what I think is the best well-rounded, all-round nice paradigm for concurrent programming. So it starts by, let's combine deterministic data flow and message passing. And in order to do that, we just need to add one concept to deterministic data flow, which is a named stream. Basically, we have to attach an ID, a constant name to a stream, and the resulting concept is called a port in the CTM book. This adds non-determinism, since any thread can send a message to the name of the stream and the message will appear on the stream. You have automatically non-determinism. Many threads sending to one stream, the messages will appear in any order. And since the named stream is still a stream, of course, it is very well integrable with deterministic data flow. So it's a seamless extension of deterministic data flow. So the resulting paradigm is called multi-agent data flow paradigm programming. This paradigm has the nice property that you can add non-determinism only where needed. You can use deterministic data flow as a default. It also has the nice property that concurrency patterns can be written very concisely. Simple example is contract net protocol, where one entity sends messages to n entities, requesting quotes. For some order, you get the results back, you pick the best one, you accept it, you reject all the others. So this gives n messages going out, n messages coming back, n messages going out again. All of this can be written in just 3 very simple lines of code in the multi-agent data flow programming using a combination of ports and functional programming patterns. We experimented to extend Scala to support multi-agent data flow. This works quite well, but it needs fine-grained concurrency to really have maximal success. It needs cheap threads. In our Ozma experiment, we implemented multi-agent data flow in an extension of Scala, but we used the Mozart runtime system because of its cheap threads. And the success was only partial on JVM because the threads are not cheap enough. So the point is that threads should be easy things. One should not be afraid of them. They should be simple and cheap to use because they are important concepts for structuring the flow of a program. And a final conclusion is that in my view, multi-agent data flow is the best all-round paradigm for concurrent programming, and it's even better than Erlang, which is quite good since it allows managing non-determinism.